We are going to do section 2.2 today, which is separating and purifying substances. There are several types of substances to separate. You can separate solids from liquids. You can separate immiscible liquids. An immiscible liquid are two liquids that are not dissolvable in each other. So, for example, like water and oil, a nonpolar and a polar substances will not mix together. Those are examples. That is an example of an immiscible liquid. We can separate solids from solids. And we can separate miscible liquids, which are liquids that do dissolve in other liquids, commonly called solutions, such as water and vinegar. So what we're going to do is we're going to go through those categories and give examples of them and how you could separate them in a lab setting. So the first one is solids from liquids. One example of separating a solid from a liquid is something called decanting, where you have, for example, let's just say down here is dirt and it's mixed with water. Decanting uses a stirring rod to pour the mixture down the stirring rod, and only the liquid will basically be pulled off the top and the solid will stay in the container on the bottom. So decanting is a very simple way to separate a solid from a liquid. Filtration is another way to separate a solid from a liquid. We did this in experiment 1.1 at the beginning of the year. You have an Erlenmeyer flask. It is connected to a Buchner funnel. You put a piece of filter paper in there. You pour your mixture here through the use of a vacuum and through gravity. The filter paper will keep the solid particles in the top. The liquid will drip down to the bottom, thus separating the solid from the liquid. So the solid stays up here, the liquid is collected in the Erlenmeyer flask. Centrifuging is another way to separate a solid from a liquid. So a centrifuge is a machine where it's often used with test tubes, and you put test tubes in this little machine right here. And the test tubes always have to be balanced, which means if you have a test tube here across from it to balance the weight, you have to have another test tube there. A centrifuge works on the rotating speed and centrifugal force, which causes the solids to settle to the bottom and then the liquid layer to stay on the top. Immiscible liquids. Immiscible liquids are liquids that do not mix, mainly due to their polarity. Oil and water is an example of an immiscible liquid mixture. They have different polarities. Water is what we call a polar molecule. Oil is what we call a nonpolar molecule. Polar and nonpolar liquids do not mix, and you can see the different layers of those liquids with the naked eye. The liquids easily are separated by letting the liquids settle to the bottom. The more dense liquid will settle to the bottom. Because they have different polarities, they will separate on their own. So for example, if you think about like a lava lamp, it has a mixture of water and some sort of oil in it. So if you let it settle for long enough, the mixture will separate on its own. Polar liquids include things such as water and vinegar. Nonpolar liquids include things such as oil and gasoline. Solids. So if you have mixtures of solids, how can you separate them? It can be based on their densities. If you have two solid substances or two solid particles, they can separate on their own based on their densities. Okay. You can use magnetic properties if one of your solids has a magnetic tendency. Iron is a magnetic metal. So if you have iron, for example, mixed in with sulfur, if you take a magnet, the iron can be separated by its attraction to the magnet. Solubility. So you can use a liquid, dissolve one of the solids, and it will leave the other solid there. So for example, if you had sugar and sand, that's a good example. So say you have a mixture of sugar plus sand. If you mix it with water, the sand will not dissolve in the water, and then the sugar will make a sugar water solution on the top. So you would or could decant the sugar water, or you could just filter the sand somehow. And so then you would be left with the sugar water here and sand in a separate container. And then to separate the sugar from the water, you could just boil the water off and evaporate it. And you could separate the sugar and sand that way. Solutions, miscible liquids. So how do you separate two liquids that are dissolved in each other if you can't even see that there's two things that are being dissolved? One way is through distillation. Distillation is the process of separating two liquids based on their different boiling points. Every liquid has a unique boiling point. So, for example, if you have water, which boils at 100 degrees Celsius, and alcohol, I'm not sure exactly what the temperature for alcohol is because there's different types of alcohol. Let's just say it boils at 90 degrees Celsius. And you have, say you have a mixture of the two, water and alcohol. When you raise the temperature at 90 degrees Celsius, the alcohol will boil off first. You collect it, you cool it and collect it, and you can have a separate tube of alcohol. And then when 100 degrees is met, the water can be separated, or you can just keep the water in the original container. Okay, the lower boiling point liquid will evaporate and then condense back into pure liquid. Use when boiling points are not similar. In other words, if you have a big difference in boiling points, like say you have like 100 degrees Celsius versus like 80 degrees Celsius, distillations work well for those differences. If your boiling points are too close, what happens, like say, for example, if you have a substance that has a boiling point of 100 degrees Celsius and one that has a boiling point of 95 degrees Celsius, there's a greater chance that some of this substance will boil with the 95 degrees substance, and so the separation won't be as pure. This is an example of a distillation apparatus. So your water and alcohol, for example, would be down here. You would heat it up using a Bunsen burner or a hot plate. At the lower boiling point temperature, that substance will start to evaporate, and then it goes through this chamber. Right here, this tube right here and this tube right here have cold water, which the purpose of the cold water is that when the vapor comes through this condenser, it's a two layers. There's an inside tube and then there's the cold water that flows on the outside of it. It condenses it back into a liquid and then it is collected over here. So cold water comes in here, cold water goes out here, and again, it's a double sort of thickness tube because in the inside is where your substance is. Fractional distillation is a type of distillation that is used when you do have boiling points that are similar. So like I said before, if you have like a boiling point of 100 degrees Celsius and it's mixed with something that has a boiling point of 95 degrees Celsius. The problem with using regular distillation is that sometimes what you collect over here may not be 100% of solution A, or of liquid A. So by using something called a fractionating column, you are able to achieve a better separation. And what a fractionating column is, it's basically a column that has a bunch of beads, for example. What the beads do is it allows a greater number of surface points for evaporation and condensing to occur, so that by the time the vapor reaches up here, it is going to be 100% of your first solution, which you can call liquid A, for example, here at the top. So the fractionating column just creates more surface area to achieve a better separation between two liquids that have similar boiling points. Chromatography. Chromatography is another method of separating a solution into different fractions. The concept behind it is that each fraction travels a different distance on a special type of paper called chromatography paper. The chromatography paper is designed with sort of similar to like capillary movement. You have a solution that you dip the chromatography paper in here. So you have a solution right here. You put your sample here, the ink spot, which would contain multiple liquids in it, and the goal is to separate those liquids to figure out what they are. You would put your chromatography paper into the water. You can also use alcohol. And what happens is that the water will start to migrate towards the end of the strip. As it migrates towards the end of the strip, it dissolves the ink spot, and then each fraction of the ink spot comes out of solution at different distances. Okay. Chromatography is used in like forensics, like if you have an unknown sample and you want to know what its components are. Chromatography was originally or used to be used for forensic investigations. The solution, again, that the chromatography paper is placed in is commonly water or alcohol. How do you actually identify the substances then? So you have, in this case, 3 different substances. How do those dots help you identify what solutions you have there? It is based on a quantitative measurement called the RF value. Each substance has a specific RF value. An RF value is just a ratio of distances. It is the distance from the start to the center of the substance spot divided by the distance from the start to the solvent front. So for example, if you place your ink dot right here and the first solution comes out at a distance of 2.5, that would be the distance from the start to the center of substance spot. So for this example, you would put 2.1 there. For the denominator, the distance from the start to the solvent front, so that would be from the start to the very last distance that the solvent evaporates at. So in this case, it is 2.8, and so you would divide those two numbers and you would get an RF value, 0.75. There is a table that has been created previously by scientists that has all the RF values for different solutions. And so you find the one that has an RF value of 0.75, and therefore you can determine what substance A is. Here's another example. So here we have, this is where our sample is, you have a blue dot and you have a yellow dot. The blue dot migrates to 3.1 centimeters. The yellow dot migrates to 5.8 centimeters. The total distance that the solvent made it to was 8.5 centimeters. So to find the RF value for the blue guy, you would take 5.8, let me erase some of this stuff, you would take, let's do the blue one first. You would take 3.1, put it in the numerator, divide it by the total distance from the start to the finish, which is 8.5, and you would get an RF value of 0.36. For the yellow substance traveled a distance of 5.8, so that's why that goes in the numerator there. And then the denominator would be the same as the previous one. The total distance is 8.5. So your RF value would be 0.72. Solubility. So a solution is made up of a solvent, the liquid, the larger part of the solution, and your solute, which is your solid or the smaller part of the solution that you are dissolving into the liquid, the larger liquid. Soluble means that a solid does dissolve in the solute, such as sugar, salt, things like that. Insoluble means the substance does not, or sorry, the solid does not dissolve, such as wax or sand. Solubility is measured in grams of your solute per 100 grams of water. So the basis for solubility, you'll see this in graphs and you'll wonder why it appears over and over again, is based on previous experiments of where they took certain amount, or they measured how many grams of the solute could be dissolved in 100 grams of water, or we know that grams is equal to mils of water, or you may see it as dissolved in 100 mils of water. This is an example of a solubility graph showing several different solutes dissolved in 100 grams of water. So here you see it over here on that side right there. And notice that it says solubility, which is the grams of the solute in 100 grams of water. That's the definition of solubility. On the x-axis, we have temperatures, and then all these different colored lines show different solutes. So for example, this line right here shows you the solubility of NaNO3. This line right here shows you the solubility of K2Cr2O7. Notice that for solids, as you increase the temperature, as you go right across the x-axis, what is happening to the solubility of these solid solutions, or most of these solid solutions? Are they increasing, or is their solubility decreasing? Their solubilities are increasing. The higher the temperature for solids, generally the more solid you can dissolve, which makes sense. If you've ever tried to dissolve sugar in water, the higher the temperature, the more solid you can put in. The solubility curve shows you the saturation of that particular solute. So what that means, we call it saturated. What that means is that for KCl, let's just use that as an example, at 50 degrees Celsius, the most KCl that you can put in the most KCl you can put in at 50 degrees Celsius would be approximately 42 grams of KCl. The saturation point of KCl at 50 degrees Celsius is therefore 42. At 90 degrees, notice that the saturation, the perfect amount of KCl that will dissolve in 100 grams of water at that temperature is approximately 55 grams. Okay, so the lines tell you their perfect saturation, when just the perfect amount of solute dissolves in 100 grams of water. There is also something called unsaturated. So what unsaturated is a point on the solubility graph that is below the saturation. So for example, if you had 10 grams of KCl at 50 degrees Celsius, you would be unsaturated because you can add more KCl at 50 degrees Celsius before you reach its saturation. So in other words, if you are below the curve, you are unsaturated. The solution is unsaturated until it reaches that blue line at that particular temperature. So an unsaturated solution would be one that is below the saturation solubility curve at that temperature. Supersaturated is where you have an excess of your solute at that particular temperature by heating it up and then cooling it down. So for example, if you had, let's do 50 degrees Celsius again, let's say you had 70 grams of KCl at 50 degrees Celsius, you would be supersaturated. So above the curve is supersaturated. Just write that down. Above the curve is super, below the curve is un, and then right on the curve is perfect saturation. Agitation increases the saturation as well as temperature. This is a solubility curve of gases. The previous one was for solids. What do you notice that is different about the solubility of gases as the temperature increases? Does the solubility of gases increase or decrease? The solubility decreases. Gases become less soluble at higher temperatures. That's one of the reasons, if you think about soda, soda has carbon dioxide gas dissolved in liquid sugar water. And one of the reasons you want to keep soda in the refrigerator is because at higher temperatures, the gases come out of solution. So you want to keep them at cold temperatures to keep the solubility higher. And when you agitate a gas in a liquid, it decreases the solubility. That makes sense. If you shake soda, the gases are agitated, they come out of solution easier. The opposite is true for solids. If you shake a solid in a liquid, its solubility increases. And that is where we will end these notes for today.